Okay, welcome to part 2 of our lesson on the vector equation of planes. And in this part, or in this video, we'll just run through some examples. So first, kind of most straightforward example is we are going to find the vector equation of a plane containing these 3 points. So one thing to notice first is that you need 3 points to define a plane. If you only had 2 points, that would define a line, but you need the third to define the plane. So we know that our vector equation xyz is going to be, we need a point plus t times a vector on the plane plus s times a vector on the plane, where t and s are real numbers. So the first thing we're going to need is 2 vectors on the plane, u and v. So how do we get a vector on the plane? Well, that's just as straightforward as it was with lines, right? If this point's a point on the plane, and this point's a point on the plane, then the vector going between them, vector AB, will be on the plane. So let's just get vector AB. So that just means we subtract our b's from our a's, or subtract, I guess, our a's from our b's. So minus 3 and negative 3. So that'll be our u, and then our v, we've got some options here. So AB is 1. We could take BC, you could also do AC. Notice you couldn't do BA because BA would not be, well, it would be in the same direction as A, not in the same direction, but it would be a multiple. So they have to be non-collinear. So BC, so just take your B's and subtract them from your C's. 5 minus 3 and 5. So therefore x, y, z is equal to, so the first thing we need is a point. You can take any of these points. Take 1, 2, 3 plus t times, let's go with the first one. And now, since these are all negative, I can do any multiple of this. So I'm going to take negative u, just so I don't have negatives. 4, 3, 3. Just to make my equation look a little nicer. But you could have used the negatives if you wanted. So t and s are real numbers. So you should always remember to write that. That's well, it's important. You know, it's something you should always write. And then if we want the parametric equations, we'll just write the components. So x is equal to 1 plus 4t plus 5s. Y is equal to 2 plus 3t minus 3s, and z is equal to 3 plus 3t plus 5s. And then again, t and s are real numbers. Okay, so you have these 3 parametric equations which correspond with this arrow, that vector equation. So that's one example. Let's make this part B. So we're going to ask, is the point point 0, 8, 1 on this line? So we're going to do something very similar to what we did for vector equations of lines. So what we did was we took the x value, put it in for x, y value for y, z value for z. So let's do that, see what happens. So my x is equal to 0. So 0 equals 4, 1 plus 4t plus 5s. So that's equation 1. Y is equal to 8. So that's another one, and 1 is equal to z. Alright, so we have this. We can simplify this a bit, right? So 0 equals 1 plus 4t plus 5s. Couldn't really simplify that one. That's equation 1. Equation 2 goes 6 plus 3t minus 3s. And equation 3 minus 2 equals 3t plus 5s. Okay, so these three equations. So now what we need to do is check that these are consistent. So are these consistent? That means, is there an s and a t which satisfy all three equations? So what we're going to do is we're going to solve 1 and 2. Nothing special about 1 and 2. Could have done 1 and 3, could have done 2 and 3. So we're going to look at these two. So we're going to solve this system. Figure out which t and s satisfy this. So that's just a linear system, right? Linear system, two unknowns. So various ways we can do this. We can do it by substitution, elimination. I'm going to go elimination. So what's my common multiple? 12. So I'm going to multiply 1 times 3. I'll have 0 equals 3 plus 12t plus 15s. And then I'm going to do 2 times 4. So what am I going to have? What happened here? Oh, sorry, I wrote this wrong. 6 is equal to 3d. So 6 times, what was it? So we'll write it like this. 0 equals negative 24 plus 12t times 4 minus 12s. And then what we're going to do to eliminate the t's is subtract these two equations. So 0 equals 27, no more t's, plus 27s. So that means 27s is equal to minus 27. Divide both sides by 27. S is equal to negative 1. Then to get t, sub into 1 or 2, whichever one you want. Sub into 1. So 1 was, what was 1? 0 equals 1 plus 4t. So 0 equals 1 plus 4t plus 5 times s. Now s, recall, is negative 1. So let's just figure out what t is now. 0 equals 1 plus 4t minus 5. So 4t is equal to, what is that, 4? So t is equal to 1. So we have t equals 1 and s equals negative 1. Okay, very good. That's the solution to this system of two equations. But now we have to check, is that consistent with this one? So what we will do is check, does s equals negative 1 and t equals 1 satisfy this? So I'll rewrite this equation. So minus 2 equals, what was it, I forget. 3t plus 5s. 3t plus 5s. So that was equation 3. So now I'm going to check if I sub this in. So on the right side, if I let s equals -1 and t equals 1, I'll have 3 times 1 plus 5 times s, which is -1. So we get 3 minus 5 equals -2, which, very good, is equal to the left side. So therefore, s equals -1, t equals 1 satisfies all 3 equations. Therefore, this point is on the line. If we had got something different than, -2, then it wouldn't be consistent, and the point would not be on the line. Exclamation mark. Okay, so what that means, just to sort of show you what it means. So that means if we let t equal -1, s equal t equal 1, s equal -1, and put that into the vector equation. Remember, this was the original vector equation right here. So t equals 1, s equals -1, we would have got this point right here. So therefore it is on the line. So that's what it means for a point to be on a line. So it's pretty tricky, right? Well, not tricky, but it's a lot of work. And if you think about how we did that for lines, it was more work to check if a point was on a line because of the extra parameter t. Remember, that t created that extra parameter, sort of a go-between between the x and y. Well, now we have 2 extra parameters. So we end up having to solve for both extra parameters, t and s. So we had to solve for both, and then check that it worked in the third. Okay. So, final example, we're going to find the y-intercept of the same line. So let me just rewrite them quick. So there were your parametric equations. So when we were in R2, the y-intercept occurred when x was equal to 0. But now we have this extra thing, z, and the y-intercept is actually going to occur when x and z are equal to 0. So what we're going to have to do is set them both equal to 0. So now we have a system of 2 equations. So I'll just rewrite 2 underneath this one. And we just need to solve the system. So I can do that by subtracting. So t is equal to 2. And then figure out what s is equal to. So I'll sub that back into, let's say, 1. So 1 was 0, 1, plus 4 times t, which in this case is 2, plus 5s. So 0 equals 1 plus 8. So 5s equals -9, so s is equal to -9 over 5. So that's my s, that's my t. Now to get y, I'm just going to sub t into this and s into this. So y is equal to 2 plus 3t minus 3s. So let's see if I can get this done in time. 2 plus 3 times 2 minus 3 times -9 over 5. 2 plus 6 plus 27 over 5. Ooh, end of page. 8, so that's 40 over 5 plus 27 over 5 equals 67 over 5 is your y-intercept. Okay, so y-intercept 67 over 5. And we get that just by letting x and z equal 0.